There's an important rule in relativity that, as far as we know, all objects must obey. If you have no rest mass as you travel through the vacuum of space, you absolutely are compelled to travel exactly at the speed of light. This is exactly true for all massless particles, like photons and gluons, approximately true for particles whose mass is tiny compared to their kinetic energy, like neutrinos, and should also be exactly true for the massless ripples in space-time created by purely gravitational effects, gravitational waves. Irrespective of whether gravity itself is inherently quantum in nature, the speed of gravity must be exactly equal to the speed of light. At least, that's a necessity if we assume that our current laws of physics are correct. And yet, when we saw the first neutron-star merger in both gravitational waves and with light, from an event that occurred some 130 million light-years away, the gravitational waves arrived first by a substantial, measurable margin, by almost 2 seconds. What's the explanation? Even though the signal originated from such a great distance away, that distance shouldn't matter. If the signals were generated at the same time and they travel at the same speed and follow the same path, then they should have arrived at the same time too. Originally, this was a puzzle with a few competing ideas attempting to explain it. However, we've now gathered enough data about these events and the rest of the universe that one explanation stands out from the rest. Here's the story of why we think that light's arrival was delayed, relative to the measured gravitational wave signal, even if those signals both traveled at the same exact speed. On August 17, 2017, the signal from an event that occurred 130 million light-years away finally arrived here on Earth. From somewhere within the distant Shell elliptical, or lenticular galaxy, NGC 4993, two neutron stars had been locked in a gravitational dance where they orbited one another at speeds that reached a significant fraction of the speed of light. As they orbited, they distorted the fabric of space owing to both their mass and their motion relative to the curved space through which they traveled. Whenever masses accelerate through curved space, they emit tiny amounts of invisible radiation that's invisible to all light-based telescopes. Gravitational, rather than electromagnetic, radiation. These gravitational waves behave as ripples in the fabric of space-time, carrying energy away from the system and causing their mutual orbits to decay. As time went on, the two neutron stars began to enspiral, with gravitational waves carrying orbital energy away, causing these two objects to migrate closer and closer together. At a critical moment in time, these two stellar remnants spiraled so close to one another that they physically touched. And what followed was one of the most spectacular scientific discoveries of all time. As soon as these two stars collided, the gravitational wave signal came to an abrupt end. Everything that the LIGO and Virgo detectors saw was from the inspiral phase up until that moment, followed by total gravitational wave silence. According to our best theoretical models, this was two neutron stars inspiraling and merging together, likely resulting in a remarkable end result, the formation of a black hole. But then it happened. 1.7 seconds later, after the gravitational wave signal ceased, the first electromagnetic light signal arrived, gamma rays, which came in one enormous burst. From the combination of gravitational wave and electromagnetic data, we were able to pin down the location of this event better than any gravitational wave event ever, to the specific host galaxy in which it occurred, NGC 4993. Over the coming weeks, light began to arrive in other wavelengths as well, as close to 100 professional observatories monitored the spectacular afterglow of this neutron star merger. On the one hand, this is remarkable. We had an event occur some 130 million light-years away, far enough away that light took 130 million years to travel from the galaxy where it occurred to our eyes. Back when the merger took place, planet Earth was a vastly different place. Feathered birds had been around for only 20 million years, placental mammals for 10 million. The first flowering plants were just beginning to emerge, and the largest dinosaurs were still yet to come into being, something that wouldn't occur until 30 million years in Earth's future. For all that time, from then until the present, both the light and the gravitational waves from this event were journeying through the universe, traveling at the only speed they could, the speed of light and the speed of gravity respectively, until they arrived at Earth after a journey of 130 million years. First, the gravitational waves from the inspiral phase arrived, moving the mirrors on our gravitational wave detectors by an incredibly small amount, less than a 10,000th of the size of an individual proton. And then, just 1.7 seconds after the gravitational wave signal ended, the first light from the event arrived as well. Immediately, this gave us the most impressive physical measurement of the speed of gravity ever. It was equal to the speed of light to better than 1 part in a quadrillion, 1015, as it takes around 4 quadrillion seconds to make up 130 million years, and they arrived less than 2 seconds apart from one another. Prior to that, we had excellent theoretical reasons for knowing that the speed of gravity ought to equal the speed of light, but only had indirect constraints that the two were equivalent to within 2% or so. The improvement on our constraints of more than 12 orders of magnitude with one single observation represents the most significant leap from a single measurement of all time. Does this mean that the speed of gravity and the speed of light aren't quite equal then? That perhaps either gravity moves slightly faster than c, the speed of light in a vacuum, or that light itself might actually move a tiny bit slower than c, as though it had a tiny but non-zero rest mass to it? That would be an extraordinary revelation, but one that's highly unlikely. If that were true, light of different energies and wavelengths would travel at different speeds, and the level at which that would need to be true is much too large to be consistent with observations. In simpler terms, if light had a non-zero rest mass, and that mass were heavy enough to explain why gravitational waves arrived 1.7 seconds earlier than light after traveling 130 million light-years across the universe, then we'd observe radio waves traveling significantly slower than the speed of light. Too slow to be consistent with what we've already observed. But that's okay. In physics, we don't have any problem considering all possible explanations for an observed puzzle. If we're doing our jobs correctly, then we'll be able to consider every fathomable explanation. Hold the data up against each one of them, and all of them will be ruled out except for one. The challenge is to find the correct explanation that fits all facets of our observations, and is still powerfully predictive for what signals should appear versus the ones that actually showed up. And we think we have. The key is to think about the objects that are merging together, the physics at play, and what signals they're likely to produce. We've already done this for the gravitational waves, detailing how they're produced during the inspiral phase and cease once the merger takes place. Now it's time to go a little deeper and think about the light. Up until these two neutron stars touched, there was no extra light produced. They simply shone as neutron stars do. Faintly, at high temperatures, but with tiny surface areas, and completely undetectable with our current technology from 130 million light-years away. Neutron stars aren't like black holes. They aren't point-like. Instead, they're compact objects, typically somewhere between 20 and 40 kilometers across, but denser than an atomic nucleus. They're called neutron stars because they're about 90% neutrons by composition, with other atomic nuclei and a few electrons at the outer edge. When two neutron stars collide, there are three possibilities that can result. They are: you can form another neutron star, which you'll do if your total mass is less than 2.5 times the mass of the Sun. You can form a new neutron star briefly, which then collapses into a black hole in under a second, if your total mass is between 2.5 and 2.8 solar masses, dependent on the neutron star's spin. Or you can form a black hole directly, with no intermediate neutron star, if your total mass is greater than 2.8 solar masses. But nevertheless, light still got out. The next question was, simply, how? How was the light that we observed generated? Again, there were three possibilities that we could think of. Immediately, as soon as the neutron stars touch, by processes that occur on their surfaces. Only after material gets ejected, where it collides with any surrounding material and produces light from that. Or from the interior of neutron stars, where reactions generate energy that only gets emitted once it propagates to the exterior. In each scenario, gravitational waves travel unperturbed once the signal is generated, but light takes an extra amount of time to get out. Although it's now 2025, and we have several direct detections of merging neutron stars through the emission of gravitational waves, GW 1.7-00817 remains the only multi-messenger event where we saw the light signals and the gravitational wave signals arriving from the same neutron-star merger. It's a testament to how incredibly precise the science of gravitational wave astronomy has become that we can reconstruct all we have. When you add in the electromagnetic follow-up observations from the 2017 event that also produced light, we've definitively shown that a large fraction of the heaviest elements in our universe, including gold, platinum, iodine, and uranium, do indeed arise from these neutron star mergers. But not perhaps from all neutron star mergers. Perhaps it's only the ones that don't immediately form a black hole that give rise to these heaviest of elements on the periodic table. Either ejected material or reactions in the neutron star's interior is required to produce these elements, and hence, the light associated with a kilonova explosion. That light is only produced after the gravitational wave signal has ended and may further be delayed by having to pass through the circumstellar material. This is why, even though light and gravity both travel exactly at the speed of light in a vacuum, the light we saw didn't arrive until nearly 2 seconds after the gravitational wave signal ceased. As we collect and observe more of these events, we'll be able to confirm and refine this picture once and for all.